second part of the 6th lecture. So in this part, we are going to build on top of what we looked at in the previous part. So in the previous part, we're looking at nothing more than while loop. A while loop. How can we use a while loop to make a block of code or instructions run repetitively, either indefinitely or a specific number of times and nothing more. So in this section, so in the previous one, we used a while loop to do that. How did we do it? So let me run my simulation again. We agreed when I press the left button, the left push button, that's all I get. I keep on getting. So guys, you watch the button for as long as it is pressed or while it is pressed. That means look at the way the circuit look at the way we've made the circuit, right? So for as long as I've pressed, GPIO PB2 or B2 in this case is going to be driven to logic low. So that is our condition. So the moment that condition comes out true, we execute which lines of code? These ones. We execute these ones, right? We execute these ones. So let me use a better notation. So I think that one makes more sense. Let me recompile. You can watch from here. Yep. All right, it's done with the compilation. So I can come here and stop, reload the firmware. So run the simulation again. So when I hold down, long and behold, it blinks indefinitely or flashes indefinitely. Now, we said this is the other logic we wanted, right? This is the other logic we wanted. So when I press and hold down the far right button, the one I called button pin R, you get the point. It only blinks. It only blinks, let's say 5 times. So I remember, because remember we created, how did we implement that, right? How did we? So we are looking more about how we implemented that in this lecture, so that we can implement it with another kind of loop. So we had our test condition. This time around, it was not only testing for whether the button has been pressed, but it had to even add a count. Add a count. You get the point. It's like saying if someone delivers, let's say you're trying to buy a phone at higher purchase, right? Or you have a shop, someone is buying a phone at higher purchase. And you're like, if they make the first deposit, that is condition 1. In our case, pressing down the button. Then you have to keep track of how much they need to keep depositing until you stop, taking their deposits and then hand over whatever they are buying, right? So guys, 5 times only. So no matter how much I press again, the condition that brings us back into the blinking or flashing state for the R LED, right? So the one responsible for the right button. So this LED, right? It does this LED right here. It does not come back. Let me show you this one. This is the one I'm talking about. So it does not come back to flash anymore after 5 times. How did we do that? So I was saying we have the first test condition. The moment it narrows down to true, we are waiting for the other condition to also be true to flash. The moment one of them or neither is true, because we're using an AND operation. Remember, an AND gate or an AND logic only outputs true or high or 1 only when both inputs are high or are true in this case. So you will find that after flashing, let's say turning on, off, let's say the condition is true. Like for the first scenario, because we initialized flash count as a global variable, right? Flash count, and it starts with 0. That means the moment I press for the very first time, flash count is equal to 0. Is 0 less or equal to 4? It is a less or equal operation. So the less part is true. 0 is less than 4. So the whole of this part comes out true. So now, is digital read button pin R equal to 0 or low? Let me use more intuitive. Or equal to, is it low? In this case, yes, because I will have pressed. So for the very first time, then we flash. We turn the LED, the R LED on, off. Then the moment we are done with doing it for the very first time, that is the flashing, right? The moment we are done with flashing, the very first time, we increment flash count by 1. So what we do is get the current value of flash count. At this moment it is equal to 0. You add 1 to it, then save it as the new value of flash count. Remember, the code execution is not going to get outside of this loop, not until these two conditions narrow down to false. So guys, pay attention closely. So the remaining sections of embedded systems are going to hinge around control structures, because we don't just randomly run a piece of code, right? It only comes out as a result of some condition being true, right? Some test condition narrowing down to true or false. So let's say you're flying a drone, right? You're flying a drone. Let's say you are trying to shoot, let's say, a wedding, right? So that drone is not going to sway to the left or to the right unless the right conditions of the flight controller are met. So the code that is controlling that drone only controls the motors, the propellers, a certain way, right? A certain way, only under specific conditions, attain a certain altitude, rotate around at, increase or decrease the pitch, increase the speed. You get the point. So everything in embedded systems evolves around control structures. So control structures help us create intent, right? To execute code with intent. So such that out of the blue, you don't see your phone shutting down. It only happens under specific conditions. If the battery is 100%, and you've not long pressed the power button for a certain time, your phone is not going to shut down. Though that piece of code is there, waiting for a specific condition to happen, then long and behold, it runs. So you better pay attention. And here is a very important segment, the loops, right? Remember I said we have if, else if, switch case, and loops. For the loops, we have a while loop. For the loops, we have a while loop, a do while, and a for loop. That is how it is for embedded C++, right? So we're back to the example. So after our test condition being true for the very first time, it's true. We run this block of code which just flashes on and off, half a second interval in between. Then we increment the variable, a global variable called flash count, which we initialized or declared all the way up top, right? Outside of setup and loop. So I've been explaining these things. So this is the part that we call the updation. So we are updating. Like I said, you're making installment payments on your iPhone 17, right? Every time you deposit, let's say $500,000, let's say 1 million, 2 million, until you raise the money that buys the phone, or Samsung S26 Ultra, Infinix, whatever, you get the point. You have to, so you do whatever you're doing, in this case deposit, then you update. You have to update. You have to keep record of that event happening. Without that record, you're going to do unnecessary work. You're going to pay, in that scenario, you're going to pay extra, or you're going to pay less. Either side is going to make a loss. You get the point. One of you is going to make a loss. The person selling the gadget, the phone, or whatever, and you who is buying it, you may overpay. So that is why we have receipts. So in this case, think of this as our receipt. Every time we execute a piece of code, this is a way of counting. That's why I put this line of code, it's at line 51. So I put this line of code only after doing the work. I can't give you a receipt for an item you've not paid for yet. Let me hope I'm making this extremely clear. Do we get the point? Let me hope I'm making this crystal clear. So every time we execute this, we could have been doing something else entirely, but at the end of it all, we must make an updation. So we update, we keep track. So flash count is like a variable that helps. I could have called it X. Its name doesn't really matter in this case. It's only there to remind us its intent. So flash count is updated by 1. Every time we execute, we count. Every time we execute, we count. Every time we execute, we count. You get the point? Every time we execute, we count. So, after updation, what happens? Because there is no any other line of code. So look at this. So the while loop starts from here and ends here. That's it. That's all we have. So after this, there is no any other line of code. It goes back to the test condition. It tests. Is the button still pressed? In this case, is the digital read at that? Because the digital read command is the one that checks the status of a GPI, or is it low or high. So by us pressing the button, we drive this GPIO, the one we've called button pin R low. So we are testing, is it low? And logical and. There is bitwise and, guys. So there is another kind of and. So logical and, right? Is this true? And is the value of flash count the current value of flash count now? Because now the value of flash count is the one we have as far as the while loop is concerned, is the one that we last updated. It's no longer 0, it is 1. Is 1 less or equal to 4? The less part is true, because since it's less or equal, so only one of these two conditions need to be true. So the less part is true. 1 is less than 4. Long and behold, we repeat again. Flash data, we keep updation. We count. Now, flash count is not 0 at this point. It is 1. Now we add 1 to it, becomes 2. We go back until flash count is equal to 4. But by the time we reach 4, because remember we started from flash count equals to 0. 0, 1, 2, 3, 4. Those are 5 times. By the time flash count is equal to 4, we will have done the flashing. We will have flashed 5 times. Now, let's see what happens. So, we run this again, because now that will be the 5th time. We run it, and no more. We don't need to run it anymore. So, we update. Flash count is no longer now 4. Now, after this line of code, flash count is equal to 5. We come back to the test condition. Is the button pin pressed? Yes, it's still pressed. And is the flash count less or equal to 4? Is 5 less than 4? Hell to the no. Is 5 equal to 4? A big no. So one of these conditions has narrowed down to false. Remember, this is an AND operation. The whole of the test condition is just going to come out as false. We never come back inside this. We never come back inside this loop. Because what happens? We get outside of the loop. So what else is there? Nothing. So we go back to the beginning. We go back to the beginning. You get the point? So that now, even when I press the other button, the other piece of code can run. The other, yes, this one is also, this other part is also being tested. Only that the condition that brings us back inside has not been met. Because yes, I've pressed, but the flash count, the last time we updated it, it was equal to 5. 5 is not less or equal to 4. Let me hope I've cleared this extremely well. Let's do something else entirely. Let's do it like this. Now, let's do it like this. Let me even change. Let me come around here and stop the simulation. Change the color to green, blue. Let me go to green. Let me go to green. Okay. So now, so that so that people get to see we are not running the old piece of code. So that it's not a gimmick. Now, let's do something else entirely. This time round, let's make a number of times. Let's make them 10, not 510. No one has that time. So now, only using a for loop, using a for loop. So using a for loop. So we get the point. So now we are using the for loop. How does it work? So remember, for the while loop, we had to create our updation. We have to cater for the block of code to execute. We have to cater for the test condition. Is the for loop any different? Hell to the no. So this is how it goes. So we start with the keyword for. Here goes a number of things. Now remember, for the while loop, we had to initialize a global variable called flash count. For a for loop, we don't necessarily have to. We can create a local variable. So let's say int. I can even call this one blink count and initialize it to 0. Guys, in computer science or advanced electronics, we start with 0, right? Yeah, digital systems start with 0. There's no way we skip 0. We start with 0. So get used to it. You can even start with 1 in this case because you're the one controlling the variable, but you'll have issues grasping many concepts like arrays, indices, memory spaces, things like that. So it's for the best we get used to starting with 0 culture. Let's make it into a culture. So int blink count, that's a variable and it's local. Why? Because it can't be accessed outside of the scope of the for loop, right? It's only accessible inside the brackets, the curly brackets of the for loop. So now, int blink count equals to 0. So now we've assigned the value 0 to a new variable, local variable called blink count. Now here comes the test condition. Here comes the test condition. So we can just come and copy this. We can come and copy and paste it there. So I'm going to expand this all the way to this side so that we can see. I will miniaturize the circuit. So this is our initialization. For it has the initialization inside of it. With it ended with a termination character. We have the test condition. 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 I will put it in extra brackets so that it does not confuse us. Right? That's now the test condition is the digital read button pin equal to low and the flash count less than. Now in this case, if we want 10 times and we are starting from 0, we must stop at 9. The value flash count must stop at 9. So in this case, we didn't call it flash count, we called it blink count. So copy and paste is the root of all evil. So you just copy and paste things without thinking, you end up in serious trouble. So now we are remaining with one other thing, the updation. The updation part. Blink count. And there is a shortcut for this. Instead of saying flash count, like for this case, flash count is equal to flash count plus 1, we just do this, plus. Long and behold, we have created. So if we have any syntax error, we better check it now. So in in embedded systems or computer science in general, it is advised not to write hundreds and hundreds of lines of code without testing them in chunks. You get the point, right? The block of code you create, you test it before you proceed. It's for the best you do it that way. Other than ending up with errors you can't even undo, you can't debug. You end up with hundreds and hundreds of bugs. So that's why yesterday I didn't write the whole thing. I wrote this part, tested it, wrote this part, it had issues, fixed them. That's how we are at this point right now. So I'm not going to do any much. Let me blink the same thing 10 times. Because now, since we have contradicting pieces of code, I'm going to comment this one out. I'm going to select it whole. I hold down the control and the /. So I comment all of these lines of code. So to the environment, it's like as if these lines of code don't exist. So it's as if these lines of code don't exist. I will leave them though. I will leave them there though when they are commented out, right? So we are going to comment that stuff out. Okay, so when we are compiling the code, this is not going to be compiled. So it's as if it's not there. Though for readability purposes, let me leave it there. Let me leave it there. So now, this is what we have. We've said we have the initialization, the test condition, and the updation. Now, what this means is that start out at a certain value equal to 0. For our case, we've called it blink count. Test whether a certain condition is true. The moment it is true, run a block of code, come and make updations, come back to the test, run, come back to updation, make the test, like that. The moment the test condition is not true, exit the loop. That is how it works. So we are just now blinking. We are now just blinking like we've agreed. Let me copy it with it. Okay. So I'll come here and do this. I uncomment it. I highlight it. I hold down the control key on the Windows machine. Most of you may be using Windows machines. For those who are using Mac, it's probably command. It's the command, right? Command button. So command / so or control /. Okay. This is what it will do. So let's hope we have no issues. Let's try to verify or compile our code. Okay, that is the board. I already selected the microcontroller. So I'll verify whether we have syntax errors or not. Because the compiler catches only syntax errors. Okay, it seems we have no syntax errors. All right, so let me come here and reload the firmware. All right, let me run the simulation. So let me drag this again. Let me drag this like so. Zoom this in so that people can see. So I'm going to hold down. So let's first test the other piece of code. Stop. Okay, run. Okay, I had not started the simulation. So let's test the other part. The other part is still functional. So we've wrote a piece of code and it's not blocking the previous lines of code. So let's test the other one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is way beyond the 10 mark we had agreed upon. Aha. Good thing when I let go, it stops. Good thing when I let go, it stops. At least we have that part right. Now, the part that we don't have right, it is that it's not stopping. It is not stopping at the 10th flash, the 10th blink. You get the point? The 10th blink. So what we are going to do is this. Let me first stop the simulation and go back to the coding area. So this is what we have. This is what we have. Let's go through the code and see how we, because now we have a semantic error. We have a semantic error because what we intended the code to do is not exactly what is happening. It's not the code's fault. It's the programmer's fault. So, and please don't be worried. This happens a lot. And if this does not happen, just know there is something wrong that is going to happen that you can't understand. Always you're going to either have a syntax error or semantic error. Either the code compiles properly and the logic is not coming out, or both are not coming out. So how do we solve the semantic? Let's first go by just going through the code line by line, scenario by scenario. So for the very first time, since we are inside the void loop, they will test this condition and it's not true. They will just get out. They will never run because I've not pressed the other button, right? Sorry. I've not pressed this button. That's why they are not running that section of code and not blinking the first LED. Okay. So now they will get to the test. They will even check for the for loop because there is nothing in between as far as the compiler is concerned. As far as the microcontroller is concerned, these lines of code don't even exist. So for ease, let me just delete them for now. So I'll come, hold on, let me cut them. It's for the best, and paste them somewhere else. So let me come and paste them down here. Okay. So this button has not been pressed, but this one has been pressed because the first thing they do is to initialize. So that means every time we run the for loop for the very first time, we have to initialize a variable. And it's a local variable because the moment I try to access it, let me show you. If I come here and say blink count is equal to, let's say 2. Let me just assign a value to it. Let me try to compile. So that we understand the idea of global and local. Yes. So the compiler is like, let's read this line of this error message. It's saying blink count was not declared in this scope. Mark the word scope. Scope, they mean inside the while loop scope. It is not known, but it is very well known. Let me cut that line of code and let me paste it. Let's sell it there. Let me compile again and see whether this time round we end up with issues or not. And we have no issues. You get the point? We have no issues whatsoever. We have no issues whatsoever. You get it? We have no issues. Because it's well known. It's well known inside the for loop. It's declared inside the for loop. So it's local to the for loop. It's not global to the whole code, so you can't access it outside. All right. So I think this kind of learning is better because if I'm to say I teach variables a different lecture, so it will not make sense. So coming up with examples, teach us the different scenarios in real time, right? So let's go through the code so that we can solve this problem whereby it's blinking way more than the times we are intending for it to flash or blink. So the very first time we enter the loop, we initialize before we even test for the very, very first time. That means blink count is equal to 0. Anywhere else if we were to talk about it, do anything with it, its initial value is 0. Then we go for the test condition, you see? It starts from there and ends there. Is the button pressed? The right button pressed? And blink count less or equal to 9. In this case, it is 0. The less part is true. So the whole of, and you've pressed, the whole of this narrows down to a true. We can't update, like I said, we can't update before doing the work. You can't ask for salary before doing your work. You can't ask for wages before doing your work. Your boss will only pay you only after you work. So let's first do what we intend to do. We flash, that's nice. On, off. Then after that, because after work, you have to go and register that you've worked. You get the point if I'm to use that example, right? If I'm to use that analogy as the example. So then you come from doing the last line of code, it's like going straight to the boss or the accountant. You make an updation, I've worked. For those who have worked on construction sites, you have to keep record of the days you work. So we increment. So by the time we increment, that means we will have finished the work. We only increment after finishing the work. So someone who is counting the number of times you've worked, they just check on this variable. Blink count. Now blink count after this point is never going to be 0. It's not equal to 0. So it's now equal to 1. So we come again and test. See if you've pressed and that value is less than 9. In this case, 1 is less than 9. It's going to come back and do that until blink count is now equal to 9. Equal to 9 will still be true, but by the time we reach to blink count is equal to 9, the number of times you will have flashed, remember we started from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are 10 times. So the system owes us another flash. It does it. Ta. Now, after that, it has to update. Then comes blink count is no longer equal to 9 because it's going to be incremented to 10. So I said blink count plus is the same as blink count is equal to blink count plus 1. All right, this is the short form. All right, so blink count plus, now the new value of blink count is 10. Is 10 less or equal to 9? No. Is 10 equals to 9? No. Since this is an AND operation, it does not matter. The test condition is going to come out false. We are not going to blink the next time. Here is the problem. We exit the loop. But since there is no any other piece of code and we left off by the time we come out here, our variable blink count is equal to 10. Is 10. Our blink count is 10. That variable has the value 10. Now, there is no any other line of code. Mark this. Let me even add it as a comment. So now we get back because the loop is done. The void loop is done. We have to go back to the top of the loop. Then we check for this. If you've not pressed it, it's not going to do anything. Now it comes back. Here is the problem now. Here is the trouble causer. This keeps on initializing. It's like a reset. It's like after paying, let's say, imagine someone paying for a motorcycle hire purchase or a loan scheme. After they've paid the 10 million shillings they've agreed upon, someone has the ability to reset what you've paid back to 0. That means they can make you pay over and over and over again. So guys, this was the trouble causer, the culprit. It keeps on initializing. How do we stop it from doing so? This is what we can do. We can remove this part but leave a termination character there. You get the point? And instead of so let's say here we can say this is one way, of doing it. We can say blink count is equal to we can even put it here, or let me do it like this. I can come at the top of the loop. Blink count is equal to 10, right? That's nice. But when I come back here, I just do it like that. I don't need to initialize it. because I've initialized it outside of the loop. So what have I done here? The moment we come here, we'll say blink count is equal to 10. You would think that stops the for loop from running the very first time. I've created another local variable, only that it's local to the void loop, but global to the for loop. Guys, I'm sorry if I'm confusing you with scopes, but this is the only way to go around the course unit. That's why I feel sorry for people who think they are going to download notes and they see it at home and then they read through while they are watching their favorite football matches. Aha. So in this case, I'm being clever about how I use the for loop. I'm creating a variable. Look at the keyword int. I'm initializing it and it's local. So I'm deliberately giving it a value that is not less and it's not equal to 9. I can even give it another value. I can even give it 100. But the moment I get inside here, I say blink count is equal to 0, right? I say blink count is equal to 0. As far as the for loop is concerned, this is its start value. And it will do whatever it was doing before. But now on the 10th, remember inside here, blink count is equal to 10. On the inside here, by the time it gets out, it will have got the value of blink count equals 10 because it first started with 0. Now, on coming back, let's see whether this saves us. This may not even save us. So guys, I'm showing you the process of going around semantic errors. Semantic errors are the ones we fear most. They are the ones we fear most as programmers, because these ones take up all your thinking capacity to solve a problem. You get the point? So by the time we're out here, blink count is 10. Now let's come back from the top of the loop. So this, by me leaving this here, it does not save us because this will happen again. What we can do is delete this completely, but still leave a space, Now take this out completely because I want it to come back. Cut. I'll cut it. I'm just going to just have it as a separate variable that starts from 0 right from top, right? Because I thought the other method was going to save us, but it's going to repeat the same thing. Because it's useless to initialize a variable only to be reset on the inside. It's going to happen over and over again. So let's start when it's equal to 0. From here. So, but this only happens at the beginning. So when we are stuck here, there is no way of updating this back to 0 because I've left this part. For the for loop, I can leave this part empty, but put a termination character. So guys, embedded systems is getting more serious, getting more involved, and it's going to get way more involved than this. And this is the only way. With notes, you will not understand anything because things are completely new to most of you. Some of you may have taken programming courses. I don't know your backgrounds, your academic backgrounds, but most of you, this is completely new, utterly new. So most of you are from high school, certificate level. You may not have gone through this computer programming courses. So these concepts are new. You better pay attention. You better watch the lectures. I'll release notes much later. And trust me, that's only when they will make a ton of sense. For now, it's just a PDF you will have that adds nothing to your life per se. So getting back to class. This is what we have. Getting back to class, this is what we have. You get the point? So I'm deliberately slowing down with examples as we go further and further. Things are going to get more detailed. Now combining so many concepts at the same time. So I've left this part blank. So that means by the time I come to the for loop, I'm just going to the test condition, updation, run, test condition, updation, run. By the moment I'm out, this will be the new value. Now, by when I come back here, blink count is not going to be changed because we are inside the scope, we are stuck inside the scope of the loop. And there is no any other line of code that changes other than this one, because this is the last line of code or instruction that updates blink count from 9 to 10. And no, that means the moment blink count is at 10, it's not going to be changed anymore. Let's try to verify this. Let's see whether this is syntactically correct. We've written correct programming grammar, what we call syntax, and it seems so. So let's test the semanticism, right? I'll come here, I'll drag this, I'll right click on my microcontroller, reload the firmware. Firmware successfully loaded, right? All right. So this is what I'm going to do. So let me put it just like so that we can see both the code and the what? And the circuit. So let us run and see whether it's doing what we want. Remember, we want 10 times only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is not coming back. And guys, I'm holding down onto the button. I'm holding down onto, because the reason is that it's not that they are not running this code again. They are testing it, only that the test condition is not true. One part of it is not true. This part is not true. Sorry, this part is not true. And we remember we are using an AND operation. The left operand and the right operand must narrow down to a true for it to give a final result as a true. So we've achieved, we can even now change this from 9 back to 4. Our 5 times of blink, right? I compile, in the meantime stop the simulation. Now I reload the firmware, run the simulation. Let me press 1, 2, 3. 1, 2, 3, 4, 5. It's not coming back, and I'm still holding. I can even press it another time. But every time I press the other one, it's always there. So this is how we implement code that runs at least once and never comes back for as long as we are running the code. Unless we unplug the power, like in this case, I stop the simulation, run it again. That's when we are back to business. The other way is hitting reset. I will add the reset part when we revisit peripherals, because the next consequent lectures are going to be more on peripherals. These commands we've been using, right? How do they operate on the inside? How do they operate on the inside? So you get the point. How do they operate? So we're going to be dealing with more detailed stuff. We're going to be looking at binary math, right? Bit math. More bitwise operators, right? Like shift, left shift operator, right shift operator, bitwise or, bitwise and, bitwise not, exclusive or. Hey. So for everyone who thinks is a little bit gumite, we have no issues with you. So you better stick around. So this, only that the good thing with this method of learning, you can come back and rewatch. You can inbox me for clarity on WhatsApp. You can inbox me. So guys, we've implemented the for loop. Now with the little time we have left, let's implement a do-while loop. A do-while loop. A do-while loop. So I will take the for loop, comment it, cut it out, and add it down here. Add it down there. So that is how it is. So now let's use, instead of a for loop, let's use a do-while loop. How do we do this? So we start with the keyword do, then while. So that is how a do-while loops looks like. So for it, all we need is this. No, this is how it's to be. I'll copy the test condition because we're still dealing with the same hardware, right? The same circuit. It's also going to flash the same GPIO. So I will uncomment it out. All right. So how does the do while operate? Do while operates in a way that is similar to a while loop, with one difference. Remember, our while loop had to first test the condition to even ever run the code once. A do-while loop is equivalent to, let's say, if you're buying, let's go back to the example of buying in installments. You're buying your iPhone, you're buying whatever, you're buying your car, right? And someone is like, the seller is like, let me give you the car without even making a single deposit. Zero deposit. I mean like zero deposit. Imagine you want to buy something. You want to buy a laptop along Kampala Road. You want to buy something from there, right? You want to buy a laptop. Let's say the new MacBook M5 or M6, right? Very expensive machine, 5-6M. And you pay zero shillings at first for an installment, zero, and someone hands you over the device. At least once. You get the point? At least once. Then comes back and checks. Did he pay? It's like letting a customer walk out of the shop, then you ask yourself later on, has he paid? You get the point? So you see how with that example, it's counterintuitive. No one in their right mind will really give you an item that you have not even if actually in real sense, in real life, they will not give it to you, not until you've cleared. But a do while is that generous. It's a very generous control structure or a very control loop that it first lets the code run at least once. The code runs at least once. Let me stress that. The code runs at least once before testing the condition. Before testing the condition. So before testing the condition, the do while loop runs this code once. So that means if we want 5 times for the thing to loop 5 times, right? We must not stop. Let's first try and see. Let me compile and see whether we have no issues. Okay, it seems okay. You have the loop starting there and stopping there. So it's saying expected while, right? Before it's expecting while before the curly bracket token. All right. Let me fix this. So guys, when I said the do while loop is kind of similar to the while loop, I got carried away. So now I'm facing the full consequences of copying and pasting. So, and I got carried away. So this is how the do while, this is how let me show you the right way of writing it. This is the right way of writing a do while. Do this. Do this while this is true. So the do while first does this at least once, then it comes for the checking. So if it finds that what it's doing, what it just did before, if it finds out that the test condition narrows down to a true, it comes back and runs again. But remember, it first ran once without even checking. Without even checking. You get the point? Without even checking. It's like dipping your hand in a rabbit hole or in an anthill without checking whether there is a rodent, a snake, or anything. You just dip in your hand, then check, is there no snake? If there isn't a snake inside, then keep the hand there. Now you've tested the condition only after running once. But the moment you detect that the hole is not empty, now you stop executing the other first action you executed. So that we have special conditions where we need such scenarios. Let me give you a quick example. A few years back, I was designing a project. I was working on a project of designing, it was actually something to do with solar. Yeah, I was designing a DC circuit breaker, a high-powered DC circuit breaker, right? So we had to first connect the load, measure the voltage and current, then detect, is it an overload or, you get the point, then maintain connection or disconnect. But we had to first connect. So a do while loop is useful when you need to first run the condition, whereby the test condition is most likely going to come as a result of first running the code. You never know. So it is a really, really special control structure or a loop, but it's very useful when you really need it. So let's compile again and see whether we have any syntax errors. So guys, I'm sorry, I got carried away, got excited, and yeah, now we've written, so do this while this is true. So I was saying now, remember it first runs once. We want 5 times. That means at least one time is going to be taken away from us. It's not even up to the condition to decide. If we want 5 times, starting from 0 to 4, we have now to start from 0 to 3. Because at least one time is always added. So let's first run the one of 4 and see whether I could be wrong. Let's compile. All right. Let's compile. Okay. Zoom in. Okay. let me stop the simulation, reload the firmware, run the simulation again. So you see, without even pressing, it's running already. It's running already. Okay, now let's see what's happening. Now, without even stopping the simulation, let me check whether guys are understanding, are following. Now, why do you think? I don't know, for those who care enough, you can comment, you can put this in the comment section, or you can inbox me and let me know, why do you think the do while, the way we've written it at this very juncture point in time, so why is it blinking indefinitely without even pressing? It does not care about my presses, because it does this once. That's nice. Now, when it comes to testing, is it pressed? No, it's not pressed. That means it shouldn't run again. And is the blink count less or equal to 4? The last time we talked about blink count was a global variable equal to 0. It is less than 4. That is nice. But I've not pressed. That means, but remember, it ran once. It ran once. You get the point? Now it exits. Since there is no any other line of code, it comes back and runs at least once. That is how we are ending up with these blinks. They are as a result of repeating the whole do loop, the whole do this. So that is the one other thing you really need to be careful about a do while loop. It may end up becoming an indefinite loop if you don't watch out for the test condition, the updation. You get the point? Let me hope you really get the point. A do while loop is very tricky to use. So let's see whether we can achieve the same results, whereby only when we press, that's when we have the do while loop. So let's do it like this. Remember, here we are not updating anything, but still it's not mattering, because had it been that we don't have anything inside here, it wouldn't be blinking. Let me comment it out and you see what I'm talking about. Let me compile again. Let me compile. I come, reload firmware. I run again. Even if I press now, because there is nothing in between there. So let me bring it back. Now, before I compile, let me do something I don't want to do as of now. Let me just try. We have something we call nested control structures. We can say if a certain condition, so let's carry the whole. Let me delete this. Confusing people. It's going to confuse colleagues. So let me paste that there. So now the do while is inside another control structure, the if. Now this, long and behold, I've introduced what the concept called nested control structures. So one control structure can only be given chance to run only if the first one under which it's being nested comes out true. What do we need to test out here for? This should run under special conditions. It should only run. And here we need to update. We should come here and update and say blink count plus plus. Blink count plus plus. Every time we work, we count. But only if we press the button at all. Because we've seen digital, that do while does not care. It keeps on running at least once. That repetitive running at least once, it turns into an indefinite flash. That's not what we want. So you see how a do while is forcing us to think and rethink, to rethink our options. So let's compile this. Let's compile. Let us compile. All right. So I'm going to reload, then run the simulation again. So 1, 2, 3, 4, 5, 6, 7. So it's going beyond and beyond and beyond. At least we've solved one portion. Right? The one that only, whereby it's blinking over and over and over and over and over. Where it's blinking over and over. Right? Where it's blinking over and over. And it does not stop. So this time around, at least we have to fast press, but it's going beyond the 5 times we want. Even way beyond. It's not stopping. You can even count as much as you want. 1, 2, 3, 4, 5, 6, 7. It's way beyond. So how do we fix this at last? How do we fix this? Because I don't need the lecture to get a little more lengthier than this. So now we have to change, because every time we update, it runs. Now here we need to let's do this. Let's try this. Let's add this. Copy. So let's verify that. So let's reload the firmware. Let's run the simulation again. Let me extend this to the other side, excuse me. So let me press 1, 2, 3, 4, 5, 6. 5, it's not going beyond that. So I will explain what just happened here, probably in the 7th lecture. In the 7th lecture, the first part of the first few 10-20 minutes of the 7th lecture, that's when I will explain what just happened here. Before we switch over to another section, I think this is where I'm going to release my first notes. Yes, I'm going to release the notes in the group. Yeah, at this very point, this lecture, this is the 6th lecture, the second part. So my first notes are all about what we've covered so far. So after explaining what just happened here, in the next lecture, we will look at something interesting. So that is all to do with control structures. Guys, this is nothing but, it is but a scratch on the surface. Just a scratch. Control structures can go in as insane as the logic needs to. If, let's say, you're developing video games, let's say you're developing code for industrial automation processes, trust me, you will come across more and more complicated logic. The only way we can wiggle our way out of such sticky and and tricky situations is through control structures. The ifs, right? The ifs, the else ifs, the loops, and loops. So with that, let's stop here for this lecture. Let's see each other let's hear from each other in the 7th lecture. Thank you.